Hello there, and welcome to the most soothing corner of the internet. Tonight we're going to drift into the gentle rhythms of our planet's climate, exploring the quiet wonders that shape the air we breathe and the seasons we cherish. These aren't the alarming headlines or urgent warnings you might expect. Instead, we'll discover the peaceful patterns, the soft cycles, and the remarkable stability that have cradled life on Earth for millions of years. Some of what we'll explore tonight will feel like a warm embrace, like learning how ocean currents carry warmth around the globe like a planetary circulatory system. Others will be surprisingly delightful, like discovering that clouds are born from the tiniest particles of dust dancing in the atmosphere. But each fact will invite you into a deeper appreciation for the intricate ballet of forces that keep our world in perfect balance. This evening, we'll wander through gentle atmospheric currents and peaceful precipitation patterns, through the slow breathing of forests and the ancient wisdom held in ice. You might find yourself growing drowsy as we explore these calming climate truths. And that's exactly as it should be. If you enjoy these peaceful journeys into science and would like more restful explorations, feel free to subscribe and let us know your thoughts in the comments below. But for now, simply settle in. Let your breathing slow and allow the tranquil science of our climate to wash gently over you. Let's begin our journey into the most relaxing climate facts nature has to offer. The Earth breathes in a rhythm that spans entire seasons. Just as your chest rises and falls with each breath, our planet inhales and exhales carbon dioxide in a gentle cycle that has continued for countless millennia. During spring and summer in the northern hemisphere, billions of leaves unfurl and begin their quiet work of photosynthesis, drawing carbon dioxide from the atmosphere like a deep, slow breath. The forests of Canada, Siberia, and Scandinavia act as the planet's lungs, absorbing vast amounts of carbon as they burst into life. Then, as autumn arrives and winter settles in, this process reverses. Leaves fall, decompose, and release their stored carbon back into the air. The Earth exhales, completing its annual breathing cycle. Scientists can measure this planetary respiration from space, watching as atmospheric carbon dioxide levels rise and fall with the changing seasons. It's a reminder that we live on a living world, one that breathes as steadily as you do right now. Water moves through our atmosphere in the most elegant dance imaginable. Every single day, the sun lifts approximately 1 trillion tons of water from the oceans, lakes, and rivers into the sky. This invisible vapor rises on warm currents, cooling as it ascends until it forms the clouds that drift peacefully overhead. These clouds are not just random collections of moisture. They're intricate structures, each droplet forming around microscopic particles of dust, pollen, or sea salt that act as tiny nuclei for condensation. The journey of a water molecule from ocean to cloud to rain and back again can take anywhere from a few days to several thousand years. Some water vapor might fall as rain within hours, while other molecules become trapped in glacial ice for centuries before returning to the sea. This endless circulation, called the water cycle, operates with such gentle persistence that it has shaped every landscape on Earth. Rivers carve valleys, rain nourishes forests, and snow caps mountains, all part of water's peaceful pilgrimage through our world. The atmosphere itself is a marvel of layered tranquility. We live at the bottom of this invisible ocean of air, in the troposphere where all weather occurs. But above us stretch layer upon layer of increasingly thin atmosphere. each with its own character and purpose. The stratosphere contains the ozone layer, that protective shield that filters harmful radiation while allowing gentle sunlight to warm our world. Higher still, the mesosphere catches meteors and burns them up before they can disturb the peace below. These atmospheric layers don't just sit there motionless. They flow and mix in patterns that span the globe, creating the jet streams that guide weather systems across continents. The jet stream itself is like a river of air meandering through the upper atmosphere at speeds that would seem violent if they weren't so high above us. But from our perspective on the ground, these powerful currents simply help deliver the gentle variety of weather that makes each day unique. Clouds form in the most delicate ways. They begin with something as simple as a particle of dust or a grain of pollen floating in the air. When water vapor encounters these tiny nuclei, it condenses around them, creating droplets so small that millions could fit in a single raindrop. These microscopic water droplets cluster together in vast, fluffy masses that drift across the sky like cotton suspended in blue. Different types of clouds tell different stories about the atmosphere's mood. Cumulus clouds, those puffy white formations that look like cotton balls, form on peaceful days when warm air gently rises and cools. Stratus clouds create those soft gray blankets that sometimes cover the entire sky, bringing the quiet comfort of overcast days. And cirrus clouds, those wispy streaks high in the sky, are made entirely of ice crystals that catch and scatter sunlight in the most beautiful ways. The temperature of our planet is regulated by an intricate system of feedback loops that work like a gentle thermostat. When the Earth gets slightly warmer, more water evaporates from the oceans, creating more clouds that reflect sunlight back into space, helping to cool things down. When it gets cooler, ice forms and reflects even more sunlight, but the system has built-in mechanisms that prevent runaway cooling. These natural balance points have kept Earth's temperature within a range suitable for life for billions of years. Ocean currents act as the planet's circulatory system, moving warm and cold water around the globe in patterns that have remained remarkably stable for thousands of years. The Gulf Stream carries warm water from the Caribbean up the eastern coast of North America and across to Western Europe, bringing mild temperatures to places that would otherwise be much colder. Meanwhile, cold currents bring nutrient-rich waters from the depths to the surface, supporting vast ecosystems of marine life. These currents don't just affect temperature. They influence weather patterns, rainfall, and even the distribution of nutrients in the ocean. The great conveyor belt of global ocean circulation moves water around the entire planet in a journey that takes about 1,000 years to complete. It's a slow, steady process that brings stability to our climate system, ensuring that no part of the ocean stays isolated for too long. Trees and forests contribute to climate in ways that go far beyond absorbing carbon dioxide. A single large tree can transpire hundreds of gallons of water into the atmosphere each day, creating its own local cooling effect. Forests create their own weather patterns, generating rainfall and moderating temperatures through the simple act of being alive. The Amazon rainforest, for instance, recycles so much water vapor that it essentially creates its own rain, sustaining itself through this gentle cycle of evaporation and precipitation. The roots of trees and plants also play a quiet but essential role in the carbon cycle. They form partnerships with microscopic fungi in the soil, trading nutrients and storing carbon deep underground where it can remain for decades or even centuries. This underground network of roots and fungi creates a vast carbon storage system that helps regulate atmospheric carbon dioxide levels naturally. Seasons exist because our planet tilts gently on its axis as it orbits the sun. This tilt of about 23.5 degrees means that different parts of Earth receive more or less direct sunlight throughout the year. As our planet travels its elliptical path around the sun, this tilt creates the gentle rhythm of seasons that has structured life on Earth for millions of years. The changing seasons bring their own climate patterns. Spring awakens plant life and begins the growing season, increasing photosynthesis and carbon absorption. Summer brings warm temperatures and active weather systems. Autumn sees the harvest and the beginning of dormancy for many plants. Winter reduces plant activity and often brings snow, which acts as an insulating blanket for sleeping vegetation, while reflecting sunlight to help moderate temperatures. Ice plays a crucial role in regulating our planet's temperature through its remarkable ability to reflect sunlight. Fresh snow can reflect up to 90% of the solar energy that hits it, compared to dark ocean water, which absorbs most of the sun's energy. This creates a natural cooling system where ice and snow help keep temperatures stable. Glaciers and ice sheets act like massive frozen reservoirs, storing fresh water for gradual release and helping to regulate sea levels over long periods. The formation of ice crystals is itself a marvel of natural engineering. Each snowflake begins as a tiny ice crystal that grows as it falls through clouds, accumulating more ice in patterns determined by temperature and humidity. No two snowflakes are exactly alike because each one follows a slightly different path through the atmosphere, encountering unique conditions that shape its final form. Natural climate variations occur in cycles that span years, decades, and even centuries. El Niño and La Niña represent shifts in ocean and atmospheric patterns across the Pacific that influence weather around the world. These cycles bring variety to our climate system, sometimes delivering extra rainfall to some regions while creating drier conditions in others. They're part of the natural ebb and flow that has characterized Earth's climate for thousands of years. Longer cycles, like changes in solar activity or subtle variations in Earth's orbit, operate over much longer timescales. These natural rhythms have guided the advance and retreat of ice ages, the rise and fall of sea levels, and the gradual migration of climate zones across the planet. They remind us that change is natural and that our planet has always been dynamic, always adjusting, always finding new points of balance. The greenhouse effect that keeps our planet warm enough for life is itself a gentle and essential process. Certain gases in the atmosphere, including water vapor, carbon dioxide, and methane, trap heat from the sun like a blanket around the Earth. Without this natural greenhouse effect, our planet would be a frozen, lifeless world with an average temperature far below freezing. The atmosphere's ability to retain just the right amount of heat has made Earth the comfortable, habitable world we know. Even the most dramatic weather events are part of natural cycles that help redistribute energy around the planet. Hurricanes and typhoons, while powerful, serve to move heat from warm tropical oceans toward cooler regions. Thunderstorms help balance electrical charges between the ground and atmosphere while delivering essential rainfall. These weather systems, viewed from the perspective of the entire planet, are simply part of the atmosphere's way of maintaining equilibrium. The carbon cycle connects every living thing on Earth in an intricate web of exchange. Plants absorb carbon dioxide and convert it into the organic compounds that form their tissues. Animals eat plants and breathe out carbon dioxide. When organisms die, they decompose and return their carbon to the soil and atmosphere. This cycle has operated for billions of years, creating a stable foundation for life while constantly recycling the basic building blocks of organic matter. Human activities have certainly influenced this ancient system, but the underlying processes remain remarkably resilient. Plants continue to photosynthesize, oceans continue to absorb and release carbon dioxide, and the great cycles of life continue their eternal dance. Understanding these natural rhythms can be profoundly calming, reminding us that we are part of something much larger than ourselves, something that has endured and adapted for eons. As we've explored these gentle climate facts, perhaps you've noticed how interconnected everything is. The water that falls as rain was once part of a cloud, which formed around a speck of dust, which was lifted by wind patterns created by temperature differences, which exist because of the sun's energy and Earth's rotation. Every process connects to every other process in an endless web of cause and effect that has been weaving itself for billions of years. This interconnectedness extends to the rhythm of your own breathing, which is part of the same atmospheric system that moves weather around the globe. The exchange of gases between your lungs and the atmosphere connects you directly to this planetary breathing system. Every exhale releases carbon dioxide that joins the global circulation, while every inhale draws in oxygen that was recently released by a tree somewhere on Earth. This invisible connection means you are literally sharing breath with forests thousands of miles away, participating in the same ancient cycle that has sustained life for countless generations. Wind patterns follow pathways that have remained surprisingly consistent for millennia. The trade winds that blow steadily across tropical oceans have guided sailing ships along the same routes for centuries. These reliable currents of air form because of temperature differences between land and sea, creating predictable flows that redistribute heat and moisture around the globe. The monsoons that bring seasonal rains to billions of people follow patterns so regular that entire civilizations have organized their agricultural calendars around them. High above the surface, winds, the jet streams carve invisible highways through the sky. These ribbons of fast-moving air meander around the planet like slow-motion rivers, guiding storm systems and weather patterns in their gentle migrations across continents. Sometimes the jet stream flows in smooth, straight lines, bringing stable weather for weeks at a time. Other times it develops lazy curves and loops, creating the atmospheric conditions that bring variety to our daily weather. The soil beneath your feet participates in climate regulation in ways that often go unnoticed. Healthy soil teems with microscopic life that processes organic matter and exchanges gases with the atmosphere. Earthworms tunnel through the earth, aerating soil and helping it absorb rainfall more effectively. Decomposing leaves and organic matter slowly release their stored carbon, feeding the next generation of plant growth. This underground ecosystem works continuously, processing nutrients and maintaining the delicate chemistry that supports all terrestrial life. Mountain ranges create their own climate zones through the simple fact of their elevation. As air masses encounter mountains, they are forced upward where they cool and release their moisture as rain or snow on the windward slopes. This orographic effect creates lush, green valleys on one side of mountain ranges while leaving rain shadows on the other. The Rocky Mountains, the Andes, and the Himalayas all demonstrate this principle, creating diverse microclimates within relatively small geographic areas. These elevation changes mean that you can experience multiple climate zones simply by driving up a mountain road. Starting in warm valleys filled with deciduous trees, you might pass through zones of coniferous forest before reaching alpine meadows and eventually barren peaks where only the hardiest plants survive. Each zone represents a different set of temperature and precipitation patterns, all created by the gentle effects of elevation on atmospheric conditions. Precipitation takes many beautiful forms beyond simple rain. Dew forms on cool mornings when water vapor condenses directly onto surfaces, creating those perfect beads of moisture that catch the early sunlight. Frost paints intricate crystal patterns on windows and leaves when water vapor freezes directly into ice. Snow arrives in countless varieties, powder to heavy, from light, wet flakes, each type determined by the specific temperature and humidity conditions it encounters during its journey from cloud to ground. Even fog is simply a cloud that has descended to ground level, transforming familiar landscapes into mysterious, ethereal scenes. Coastal fog forms when warm, moist air moves over cooler ocean waters, creating those iconic, misty conditions that roll in from the sea. Valley fog develops on calm, clear nights when cool air settles into low-lying areas, often dissipating gracefully as the morning sun warms the air. The daily cycle of heating and cooling creates gentle rhythms that influence everything from bird migration patterns to the timing of flower blooms. As the sun rises, it warms the ground, which in turn warms the air above it, creating thermals that birds use for effortless soaring. As evening approaches and temperatures cool, many plants release their stored fragrances, creating those distinctive scents of twilight that vary from season to season. Humidity levels fluctuate in response to these daily temperature changes, creating the comfortable variation between the crisp dryness of morning air and the softer moisture of evening. These natural cycles have guided the evolution of countless species, from nocturnal animals that emerge as temperatures cool to morning flowers that open with the rising sun. Polar regions play an essential role in global climate regulation through their vast expanses of ice and snow. The Arctic and Antarctic act like massive air conditioning systems for the planet, reflecting solar energy back into space and creating the cold air masses that eventually moderate temperatures in lower latitudes. The seasonal advance and retreat of sea ice creates habitat for unique ecosystems, while influencing ocean circulation patterns around the globe. Aurora displays in polar regions represent the gentle interaction between Earth's magnetic field and charged particles from the sun. These dancing lights in the sky are actually a visible sign of our planet's protective magnetic shield deflecting solar radiation. The same magnetic field that creates these beautiful light shows also helps preserve our atmosphere by preventing it from being stripped away by solar wind. Wetlands and marshes serve as natural climate moderators through their ability to absorb and slowly release water. During heavy like giant sponges, soaking lands act rains, wet up excess water and preventing floods. During dry periods, they gradually release this stored water, maintaining stream flows and local humidity levels. The plants in wetlands also process vast amounts of carbon and other nutrients, helping to maintain water quality while supporting incredible biodiversity. These waterlogged environments create their own microclimates, often staying cooler in summer and warmer in winter than surrounding areas. The constant evaporation from wetland surfaces creates local humidity that can influence weather patterns for miles around, demonstrating how even relatively small geographic features can have far-reaching climate effects. Deserts, despite their reputation for harshness, demonstrate remarkable stability in their climate patterns. The clear skies that characterize desert regions allow for dramatic temperature swings between day and night. But these extremes follow predictable patterns that desert life has adapted to over millions of years. The lack of cloud cover means that heat radiates away quickly after sunset, creating those surprisingly cool desert nights even in the warmest climates. Desert plants have evolved ingenious strategies for dealing with these climate extremes. Some store water in thick, waxy leaves or stems. Others have developed extensive root systems that can detect and collect moisture from rare rainfall events. These adaptations represent millions of years of fine-tuning to specific climate conditions, creating ecosystems that thrive in what might seem like impossible conditions. Coastal areas enjoy some of the most stable and pleasant climates on Earth due to the moderating influence of large bodies of water. Oceans heat up and cool down much more slowly than land, creating a thermal buffer that prevents extreme temperature swings. This maritime influence extends inland for varying distances depending on local geography, creating those famously mild climates found in coastal regions around the world. The daily cycle of sea and land breezes provides natural air conditioning for coastal communities. During the day, land heats up faster than water, creating pressure differences that draw cool ocean air inland. At night, the process reverses as the land cools more quickly than the sea, creating gentle offshore breezes that carry the day's accumulated heat back out over the water. Cloud formations follow patterns that have inspired artists and poets for centuries. Cumulus clouds build upward like great towers when atmospheric conditions are unstable, sometimes growing into the magnificent thunderheads that bring afternoon showers. Stratocumulus spreads across the sky in layers, creating those overcast days that filter sunlight into soft, even illumination. Cirrus clouds streak across the upper atmosphere like brushstrokes, often indicating changes in weather patterns days in advance. Each type of cloud represents a different set of atmospheric conditions, and learning to read these sky signs connects us to the ancient human tradition of weather prediction. Sailors and farmers have long used cloud patterns to anticipate weather changes, understanding that the sky tells stories about the invisible forces shaping our climate. The rhythm of seasons creates a natural calendar that has guided human activities for thousands of years. Spring brings longer days and warming temperatures that trigger the emergence of new growth. Summer delivers the energy needed for plants to grow and reproduce. Autumn provides the harvest season when plants concentrate their energy into seeds and fruits. Winter offers a time of rest and dormancy that allows ecosystems to conserve energy for the next cycle of growth. These seasonal rhythms extend beyond temperature changes to include variations in daylight, precipitation patterns, and atmospheric pressure. The subtle shifts in solar angle throughout the year create the changing quality of light that photographers and artists have long celebrated. Even the air smells different in each season, carrying the distinctive sense of growing plants in spring, warm earth in summer, decomposing leaves in autumn, and the clean crispness of winter air. Temperature gradients drive the circulation patterns that distribute heat around our planet in the most efficient ways possible. Warm air rises, creating areas of low pressure, while cool air sinks, creating high pressure zones. These pressure differences generate the winds that carry weather systems across continents and oceans. The Coriolis effect, caused by Earth's rotation, adds a gentle spiral to these movements, creating the characteristic swirling patterns we see in satellite images of storm systems. This global circulation creates predictable climate zones from the tropical regions near the equator to the polar regions at high latitudes. Each zone has its own characteristic patterns of temperature, precipitation, and seasonal variation, yet they all connect to form a single, integrated climate system. Understanding these connections helps us appreciate how local weather events are part of much larger patterns that span the entire globe. The movement of air masses across continents follows ancient pathways carved by mountain ranges, valleys, and the temperature differences between land and sea. These invisible rivers of air carry moisture from distant oceans, bringing rain to inland areas thousands of miles from the nearest coast. A storm system born over the Pacific Ocean might travel across the Rocky Mountains, gather moisture from the Great Lakes, and eventually deliver rainfall to the Atlantic seaboard, connecting ecosystems across an entire continent through the simple movement of water vapor. These traveling weather systems create the gentle variety that makes each day's climate unique while maintaining the underlying patterns that define regional climates. The storm tracks that bring winter snow to northern regions and summer thunderstorms to the plains have remained remarkably consistent over centuries, creating the reliable seasonal patterns that ecosystems depend upon for survival. Atmospheric pressure changes so subtly that we rarely notice them, yet these invisible fluctuations drive all weather patterns on Earth. High-pressure systems bring clear skies and stable conditions, while low-pressure areas create the atmospheric lifting that forms clouds and precipitation. The gentle rise and fall of atmospheric pressure creates a rhythm as fundamental to weather as heartbeats are to circulation, pumping energy through the atmosphere in slow, steady cycles. Barometric pressure changes can be so gradual that they span several days, creating those extended periods of settled weather that bring week after week of similar conditions. Other pressure changes happen more quickly, bringing the variety of weather fronts that create our daily climate surprises. These pressure waves move across the landscape like invisible ocean swells, carrying the energy that shapes our atmospheric environment. The evaporation of water from plant leaves, called transpiration, creates a cooling effect that can lower local temperatures by several degrees. A mature oak tree can transpire hundreds of gallons of water on a hot summer day, essentially air conditioning the space beneath its canopy. Forests amplify this effect across vast areas, creating their own cooler microclimates that can influence regional weather patterns. This plant-based cooling system works most efficiently during the hottest parts of the day, precisely when cooling is most needed. As leaves absorb sunlight for photosynthesis, they simultaneously release water vapor that carries away excess heat, creating a natural balance between energy absorption and temperature regulation. Gardens, parks, and urban forests all contribute to this gentle cooling effect, making cities more comfortable during warm weather. Snow accumulation in mountain watersheds creates natural water storage systems that release their contents gradually throughout the year. Winter snowpack acts like a massive, distributed reservoir, storing water during the cold months and releasing it slowly as temperatures warm. This natural timing provides steady water supplies during the growing season, when plant and animal life most need reliable moisture. The melting process itself is remarkably gentle, with snowpack typically releasing water over a period of several months rather than all at once. This gradual release prevents flooding while maintaining stream flows well into the dry season. Mountain snowpack systems have been providing this service for millions of years, creating the reliable water cycles that support ecosystems from alpine meadows to desert oases fed by mountain streams. Climate stability emerges from countless feedback loops that automatically adjust to maintain balance. When temperatures rise, increased evaporation creates more clouds that reflect sunlight away from Earth. When temperatures fall, less evaporation means fewer clouds and more solar heating reaches the surface. These self-regulating mechanisms have kept Earth's climate within bounds suitable for life throughout most of the planet's history. Ocean temperatures change much more slowly than land temperatures, creating a vast thermal reservoir that moderates climate extremes. The heat capacity of water means that oceans can absorb enormous amounts of energy during warm periods and release it gradually during cooler times. This oceanic thermal mass acts like a planetary thermostat, preventing the rapid climate swings that would otherwise make life much more challenging. Prevailing wind patterns create distinct climate characteristics in different regions around the world. The steady trade winds of tropical regions bring consistent weather patterns that have supported complex ecosystems for millions of years. The westerly winds of mid-latitudes carry storm systems from west to east, creating the familiar weather patterns that most people in temperate regions experience. The polar easterlies help distribute cold air masses that maintain the ice caps and frozen landscapes of high latitudes. These wind patterns exist because of the fundamental physics of a rotating planet heated unevenly by the sun. The consistency of these patterns over time has allowed life to adapt and thrive in each climate zone, creating the rich diversity of ecosystems we see today. From tropical rainforests that depend on steady moisture from trade winds to temperate grasslands shaped by westerly storm tracks, wind patterns have sculpted the biological landscape of our planet. The water vapor in the atmosphere carries an enormous amount of energy in the form of latent heat. When water evaporates, it absorbs energy, cooling the surface. When it condenses back into liquid form in clouds, it releases that energy, warming the surrounding air. This invisible energy transport system moves heat from warm regions, where evaporation occurs, to cooler regions where condensation happens, creating one of the most efficient heat distribution systems imaginable. Hurricanes and tropical cyclones represent this energy transport system operating at its most dramatic scale. These storms gather energy from warm ocean waters and transport it toward higher latitudes, helping to balance the energy budget between tropical and polar regions. While individual storms can be destructive locally, they serve an important function in the global climate system by preventing even greater temperature imbalances from developing. Soil moisture levels influence local climate through their effects on evaporation and plant growth. Moist soils support lush vegetation that transpires water and creates local cooling effects. Dry soils reflect more sunlight and support less vegetation, leading to warmer local temperatures. These soil-climate interactions create feedback loops that can persist for years, with wet years leading to increased vegetation and continued moisture retention, while dry years can create conditions that perpetuate drought. Agricultural practices that maintain soil moisture, such as cover cropping and reduced tillage, can help moderate local climate effects while supporting more productive farming systems. The relationship between soil health and climate stability demonstrates how land management practices can work with natural systems to create more resilient landscapes. lightning serves as nature's way of balancing electrical charges that build up in the atmosphere. The billions of lightning strikes that occur around the world each day help maintain the electrical equilibrium between Earth's surface and the upper atmosphere. This global electrical circuit operates continuously, with lightning essentially acting as a release valve that prevents the buildup of dangerous charge imbalances. The nitrogen fixed by lightning strikes provides essential nutrients for plant growth, creating another connection between weather systems and the biological processes that sustain life. Each lightning bolt converts atmospheric nitrogen into forms that plants can use, contributing to the fertility of ecosystems around the world. This natural fertilization process has been supporting plant growth for millions of years, long before humans discovered how to manufacture nitrogen fertilizers. Seasonal migration patterns of animals follow climate cues that have remained reliable for countless generations. Birds time their migrations to take advantage of favorable winds and weather patterns while avoiding harsh conditions. Whales follow ocean currents and temperature gradients as they move between feeding and breeding grounds. These migration routes represent millions of years of evolutionary fine-tuning to work with natural climate patterns rather than against them. The timing of these migrations has become so precise that many cultures have used animal behavior as indicators of seasonal changes. The return of certain bird species signals spring planting time, while the movement of other animals indicates the approach of winter weather. These biological calendars demonstrate the deep connections between climate patterns and the rhythms of life. Permafrost in polar regions acts as a massive carbon storage system, locking away organic matter in frozen ground for thousands of years. This frozen soil contains the remains of plants and animals that lived during past climate periods, preserving a record of ancient ecosystems while keeping their carbon out of the atmospheric cycle. The stability of permafrost regions contributes to global climate stability by maintaining these long-term carbon stores. The formation of permafrost occurs gradually over many years as organic matter accumulates faster than it can decompose in the cold conditions. This process creates unique ecosystems adapted to the extreme conditions, including specialized plants and animals that have evolved to thrive in these challenging environments. Permafrost regions represent some of the most pristine and stable ecosystems on Earth. Coral reefs create their own climate microenvironments through their effects on local water temperature and circulation. The complex three-dimensional structure of coral reefs creates areas of calm water and gentle currents that support incredible biodiversity. These reef systems also influence local weather patterns by affecting evaporation rates and sea surface temperatures in their vicinity. The symbiotic relationship between corals and algae represents one of nature's most elegant climate adaptations. The algae provide nutrients to the corals through photosynthesis, while the corals provide protection and nutrients to the algae. This partnership has allowed reef systems to thrive in nutrient-poor tropical waters for millions of years, creating some of the most productive and stable ecosystems on Earth. Valley climates often differ dramatically from surrounding areas due to the way terrain shapes air movement and temperature patterns. Cold air naturally flows downhill and collects in valleys, creating cooler microclimates that can support different plant and animal communities than nearby hilltops. This temperature inversion effect means that valleys often experience frost when surrounding areas remain frost-free, creating unique growing conditions. Wine regions around the world take advantage of these valley climate effects, using the natural temperature variations to create optimal growing conditions for different grape varieties. The same principles apply to natural ecosystems where valley bottoms might support moisture-loving plants, while nearby slopes host drought-adapted species, all within a relatively small geographic area. The albedo effect, or the reflection of sunlight from different surfaces, plays a crucial role in maintaining Earth's energy balance. Fresh snow reflects up to 90% of incoming solar radiation, while dark ocean water absorbs most of the sun's energy. This natural variation in surface reflectivity helps regulate temperature by ensuring that bright, reflective surfaces stay cool, while dark surfaces absorb the energy needed to drive weather systems. Seasonal changes in albedo, such as the annual cycle of snow, cover, and vegetation growth, contribute to the natural rhythm of climate patterns. Spring brings darker surfaces as snow melts and vegetation emerges, increasing solar absorption and accelerating warming. Autumn brings lighter surfaces as leaves fall and snow begins to accumulate, increasing reflection and supporting the transition to cooler conditions. Atmospheric rivers transport vast amounts of water vapor across oceans in narrow bands of moisture that can stretch for thousands of miles. These invisible rivers in the sky carry more water than the Amazon River, delivering essential precipitation to coastal regions around the world. When atmospheric rivers encounter mountain ranges, they release their moisture as rain or snow, providing crucial water supplies for entire regions. The formation of atmospheric rivers depends on specific patterns of temperature and pressure that create channels for moisture transport. These weather patterns have been operating for millions of years, creating the reliable precipitation patterns that support coastal forests and mountain ecosystems. Understanding atmospheric rivers helps explain how water moves around the planet in patterns that connect distant oceans to inland watersheds through the simple physics of evaporation and condensation. The formation of these moisture highways requires a delicate balance of atmospheric conditions that have remained remarkably stable throughout Earth's climate history. Temperature differences between warm tropical waters and cooler polar regions create the pressure gradients that guide these rivers of vapor along predictable paths. The gentle persistence of these patterns means that regions like the Pacific Northwest receive their winter rains from atmospheric rivers that follow routes established thousands of years ago. Dew point temperature represents the invisible threshold where water vapor decides to transform back into liquid form. This magical temperature varies with humidity levels, creating those perfect morning conditions when grass becomes jeweled with tiny droplets of condensation. The dew point acts like nature's thermostat for comfort, determining whether air feels dry and crisp or soft and humid. When air temperature and dew point are far apart, the atmosphere feels dry and stable. When they converge, the air becomes saturated with moisture, ready to form clouds, fog, or gentle precipitation. Understanding dew point helps explain why some summer evenings feel comfortable while others feel heavy and oppressive, even at the same temperature. Desert regions typically have very low dew points, creating that characteristic dry heat that allows rapid cooling after sunset. Tropical regions maintain high dew points that create the consistently warm, humid conditions that support lush rainforest ecosystems year-round. Thermal columns rise invisibly from sun-warm surfaces, creating the updrafts that soaring birds use for effortless flight. These columns of warm air form when the sun heats different surfaces at different rates throughout the day. Dark pavement, bare soil, and rocky outcrops create stronger thermals than forests or water bodies. Hawks, eagles, and other large birds have learned to read these invisible air currents, circling within thermals to gain altitude without expending energy flapping their wings. These same thermal currents help form the cumulus clouds that dot fair weather skies. As warm air rises in thermals, it cools and eventually reaches the dew point where water vapor condenses into visible droplets. The result is those puffy white clouds that seem to materialize from clear blue sky, each one marking the top of an invisible column of rising air. On calm days, you can often see these clouds forming and dissipating in slow motion as thermal activity strengthens and weakens with the sun's angle. Ground temperature varies in fascinating ways that create microclimates within very small areas. South-facing slopes receive more direct sunlight and warm more quickly than north-facing slopes, sometimes creating temperature differences of 10 or 15 degrees within a few hundred yards. These variations support different plant communities on opposite sides of the same hill, demonstrating how climate operates at the most local scales. Urban areas create their own unique temperature patterns through the materials and structures that cover the landscape. Concrete and asphalt absorb and retain heat differently than soil and vegetation, creating the urban heat island effect that can make cities several degrees warmer than surrounding rural areas. However, parks, trees, and green spaces within cities create cooling islands that moderate these effects, showing how thoughtful planning can work with natural climate processes. Frost formation requires a precise combination of clear skies, calm winds, and temperatures that drop just below the dew point. These conditions often occur on the most beautiful autumn and spring nights when high-pressure systems bring crystal, clear air and gentle settling of cold temperatures into low-lying areas. The intricate patterns that frost creates on windows and leaves represent the unique conditions present at each specific location, with no two frost formations exactly alike. Radiation frost forms when surfaces lose heat to the clear night sky faster than air can replace it, creating those magical mornings when car windshields and grass blades are painted with ice crystals, while air temperatures remain above freezing. This process demonstrates how local conditions can create their own climate effects independent of regional weather patterns. Sea surface temperatures change slowly but influence weather patterns across entire ocean basins. The thermal mass of ocean water means that it takes enormous amounts of energy to change water temperature even by a few degrees. This thermal inertia creates stability in climate systems, preventing rapid swings that would disrupt marine ecosystems and coastal weather patterns. Warm ocean currents like the Gulf Stream maintain their temperatures across thousands of miles of travel, bringing tropical warmth to regions far from the equator. Ocean temperature patterns also influence the formation and intensity of storm systems. Hurricanes draw their energy from warm water, but they also help cool the ocean by stirring up deeper, cooler water and increasing evaporation rates. This creates a natural feedback system that prevents ocean temperatures from rising without limit while providing the energy needed to drive global weather patterns. Pressure systems move across the landscape like slow, invisible waves, bringing the variety of weather that creates our daily climate experience. High-pressure areas, or anticyclones, rotate slowly in a clockwise direction in the northern hemisphere, bringing generally clear skies and stable conditions. Low-pressure systems, or cyclones, rotate counterclockwise and create the lifting motion needed for cloud formation and precipitation. The boundary zones between these pressure systems, called fronts, bring most of the dramatic weather changes we experience. The movement of these pressure systems follows patterns influenced by the jet stream, mountain ranges, and the distribution of land and water. Weather forecasters can track these systems days in advance because they follow predictable paths influenced by the same physical forces that have shaped weather patterns for millions of years. Understanding these pressure patterns helps explain why weather often arrives in waves, with several days of similar conditions followed by changes that bring new patterns. Sublimation allows ice to transform directly into water vapor without melting, creating some of the most subtle climate effects in nature. This process occurs constantly in snowy regions, slowly reducing snowpack even when temperatures never rise above freezing. Sublimation creates the dry, powdery snow conditions that skiers prize, while also contributing moisture to the atmosphere that can later fall as precipitation in distant locations. The energy required for sublimation comes from solar radiation and wind movement across snow surfaces. This gradual process helps explain how mountain snowpack can diminish even during cold weather, and why snow-covered regions often have higher humidity levels than you might expect. Sublimation also plays a role in the formation of certain cloud types at high altitudes, where ice crystals transform directly between solid and vapor phases. Vegetation patterns reflect long-term climate averages in ways that create natural maps of environmental conditions. Tree lines on mountains mark the elevation where temperature and growing season length become limiting factors for forest growth. Prairie grasslands exist in regions where precipitation patterns favor grasses over trees, while desert scrublands indicate areas where water availability determines plant survival strategies. These vegetation boundaries shift gradually over time as climate patterns change, but they represent averages taken over many decades or centuries. A forest boundary that seems fixed in human timescales actually represents the accumulated effects of thousands of growing seasons, each slightly different but adding up to create the conditions that determine which plants can survive in each location. Evapotranspiration combines the water loss from soil evaporation with water released by plant transpiration, creating a measure of how much moisture the atmosphere gains from terrestrial surfaces. This combined process varies dramatically with temperature, humidity, wind speed, and the type and density of vegetation present. Dense forests in humid climates can release enormous amounts of water vapor, while sparse desert vegetation contributes relatively little moisture to the atmosphere. The rate of evapotranspiration influences local humidity levels and can affect the formation of afternoon thunderstorms in many regions. Areas with high evapotranspiration rates often experience increased cloud formation and precipitation, creating positive feedback loops that maintain moist conditions. This process helps explain why deforestation can lead to reduced local rainfall and why irrigation can sometimes increase precipitation in arid regions. Inversion layers in the atmosphere create stable conditions where warm air sits above cooler air, preventing the normal mixing that occurs when temperature decreases with altitude. These inversions can trap moisture, pollutants, and even sound waves close to the ground, creating unique atmospheric conditions. Temperature inversions often form on clear, calm nights when the ground cools rapidly while upper air layers remain warm. Valley inversions create some of the most dramatic examples of this phenomenon, with cold air pooling in low areas while nearby hilltops remain warm. These conditions can persist for days during stable weather patterns, creating foggy valleys while surrounding areas enjoy clear skies. the trapped air in inversions moves very little, creating almost stagnant atmospheric conditions that can feel remarkably still and peaceful. Relative humidity describes the amount of water vapor in the air compared to the maximum amount that air can hold at a given temperature. This relationship means that relative humidity can change dramatically even when the actual amount of water vapor remains constant, simply because warmer air can hold more moisture than cooler air. Morning dew forms when overnight cooling raises relative humidity to 100%, forcing excess water vapor to condense onto surfaces. The daily cycle of relative humidity typically sees lowest values in mid-afternoon when temperatures peak, and highest values just before dawn when temperatures reach their minimum. This natural rhythm affects everything from plant water uptake to human comfort levels, creating the familiar pattern of crisp morning air that gradually becomes more humid as the day progresses, then freshens again as evening temperatures cool. Boundary layer meteorology examines the lowest portion of the atmosphere where the effects of Earth's surface directly influence air movement and temperature. This boundary layer, typically extending from the surface up to about a kilometer high, contains the air we live and breathe in daily. Surface friction, heating, and cooling create turbulence and mixing within this layer that affects everything from wind patterns to pollution dispersion. The height and characteristics of the boundary layer change throughout the day as surface heating creates convective mixing during daylight hours. Then stable conditions develop at night when the ground cools. These daily changes in boundary layer behavior influence local weather patterns and help explain why many climate phenomena follow predictable daily cycles. Latent heat transfer through evaporation and condensation moves enormous amounts of energy through the climate system without any change in temperature. When water evaporates from ocean surfaces, it absorbs energy that gets transported with the water vapor until condensation releases that same energy elsewhere in the atmosphere. This invisible energy transport system can move more heat than all the world's rivers combined, making it one of the most important mechanisms for redistributing solar energy around the planet. Tropical regions export vast amounts of energy through evaporation, while polar regions receive energy when water vapor condenses and freezes. This energy transport helps moderate temperature differences between different latitudes, preventing Earth from developing the extreme temperature gradients that would exist if heat could only move through direct air currents and ocean currents. Phenology studies the timing of natural seasonal events like leaf emergence, flowering, and bird migration in relation to climate patterns. These biological calendars have tracked climate variations for millions of years, with species adapting their life cycles to take advantage of optimal conditions for growth and reproduction. The timing of spring leaf out, for example, represents each plant species' assessment of when conditions are suitable for photosynthesis and growth. Climate change research often uses phenological records to understand how species respond to shifting temperature and precipitation patterns. Trees, flowers, and migrating animals serve as living instruments that measure climate conditions and translate them into biological responses. These natural calendars provide some of our longest and most detailed records of how climate varies from year to year and decade to decade. Mesoclimates exist at intermediate scales between local microclimates and regional climate patterns, often influenced by geographic features like lakes, hills, or urban areas. A large lake, for example, creates a mesoclimate that extends several miles inland, moderating temperatures and affecting precipitation patterns through lake effect processes. Similarly, mountain ranges create mesoclimatic zones on their windward and leeward sides that can persist for dozens of miles from the actual peaks. These intermediate-scale climate patterns often determine the success or failure of agricultural activities and natural ecosystems. Wine-growing regions rely on mesoclimatic conditions that provide just the right combination of temperature, precipitation, and seasonal variation. Natural areas like prairies and forests exist within mesoclimatic zones that provide suitable conditions across large enough areas to support sustainable ecosystems. Convective processes drive many of the most important climate mechanisms through the simple physics of warm air rising and cool air sinking. This convective circulation creates everything from daily sea breezes to the massive storm systems that transport energy across continents. Convection operates at all scales, from the tiny dust devils that form over hot pavement to the global circulation patterns that distribute heat from equatorial regions toward the poles. Understanding convective processes helps explain why afternoon thunderstorms are common in many climates, why mountain slopes often experience upslope winds during the day, and why certain geographic locations are prone to specific types of weather patterns. The predictable nature of convective processes provides stability to climate systems, while creating the variety and movement that make weather interesting and dynamic. Heat capacity differences between land and water create some of the most reliable and persistent climate patterns on Earth. Water requires much more energy than land to change temperature, which means that oceans, large lakes, and even rivers moderate the climate of nearby areas by absorbing heat during warm periods and releasing it during cool periods. This thermal buffering creates the maritime climates that characterize coastal regions around the world. Continental interiors, far from the moderating influence of large water bodies, experience more extreme temperature variations both daily and seasonally. These continental climates feature hot summers and cold winters, with rapid temperature changes when weather systems move through. The contrast between maritime and continental climates demonstrates how fundamental physical properties like heat capacity shape the climate patterns that influence billions of people worldwide. The diurnal temperature range, or the difference between daily maximum and minimum temperatures, varies dramatically with geographic location, season, and weather patterns. Desert regions often experience large diurnal ranges because clear, dry air allows rapid heating during the day and efficient cooling at night. Humid regions typically have smaller diurnal ranges because water vapor in the air absorbs and re-radiates heat, moderating both daytime heating and nighttime cooling. Cloud cover also strongly influences diurnal temperature range, with overcast conditions creating smaller temperature swings by blocking some daytime solar heating while reducing nighttime radiative cooling. Understanding these patterns helps explain why some locations experience dramatic temperature changes throughout the day, while others maintain relatively steady conditions, creating different rhythms of daily climate variation that influence everything from plant growth to human comfort. Human circadian rhythms have evolved to match these daily temperature cycles, with our body temperatures naturally rising and falling in sync with the diurnal patterns that have characterized Earth's climate for millions of years. This biological connection to daily temperature rhythms demonstrates how deeply we are embedded in the natural climate systems that surround us. Our internal clocks, synchronized with the same solar heating and cooling cycles that drive weather patterns around the globe. Temperature gradients between different air masses create the atmospheric instability that generates weather fronts and storm systems. When warm, moist air encounters cooler, drier air, the boundary between them becomes a zone of active weather formation. These frontal systems can extend for hundreds of miles and persist for days as they move across continents, bringing the variety of precipitation and wind patterns that create our changing weather. The strength of these temperature contrasts determines the intensity of the weather systems they produce. Gentle gradients create weak fronts with light precipitation and gradual changes, while strong gradients can produce severe thunderstorms, heavy snow, or powerful wind events. The seasonal cycle of strengthening and weakening temperature contrasts helps explain why certain types of weather are more common at specific times of year. Atmospheric stability describes the tendency of air to remain in its current vertical position or to move up or down when displaced. Stable atmospheres resist vertical motion, creating conditions that favor stratified cloud formations and gentle, steady weather patterns. Unstable atmospheres promote vertical air movement, leading to cumulus cloud development and the convective processes that create thunderstorms and other active weather. The degree of atmospheric stability changes throughout the day as surface heating creates instability during afternoon hours. Then stability returns as evening cooling eliminates the temperature contrasts that drive vertical air movement. These daily stability cycles help explain why many weather phenomena follow predictable timing patterns, with thunderstorms more common in late afternoon and fog more likely during early morning hours. Pressure gradient force drives all wind movement by creating the pressure differences that cause air to flow from high-pressure areas toward low-pressure areas. The strength of these pressure gradients determines wind speed, while the direction of pressure change determines wind direction. The Coriolis effect, caused by Earth's rotation, deflects moving air to create the curved wind patterns we observe in weather systems. These pressure-driven winds transport heat, moisture, and energy around the globe, creating the circulation patterns that redistribute solar energy from equatorial regions, where it is abundant, to polar regions where it is scarce. The consistent operation of pressure gradient forces over millions of years has created the reliable wind patterns that define climate zones and support the ecosystems adapted to each region's characteristic conditions. Radiative cooling occurs when surfaces lose heat to space through infrared radiation, creating the nighttime temperature drops that balance daytime solar heating. Clear skies allow efficient radiative cooling, while clouds trap outgoing radiation and moderate nighttime temperature decreases. This process operates continuously, with every surface on Earth constantly radiating energy to space, while simultaneously receiving radiation from the sun and atmosphere. The balance between incoming solar radiation and outgoing infrared radiation determines Earth's overall temperature and creates the energy budget that drives all climate processes. Small changes in this radiative balance can have large effects on global temperature, but natural feedback mechanisms have maintained this balance within relatively narrow bounds throughout most of Earth's history, creating the stable conditions that have allowed life to evolve and flourish. Vapor pressure equilibrium governs the delicate dance between liquid water and water vapor in the atmosphere, creating the invisible threshold where molecules decide whether to remain in liquid form or escape into the gaseous state. This equilibrium point varies with temperature, explaining why puddles evaporate more quickly on warm days, and why your breath becomes visible on cold mornings. The constant exchange of molecules between liquid and vapor phases creates a dynamic balance that has remained stable for millions of years, supporting the water cycle that sustains all terrestrial life. Understanding vapor pressure helps explain many of the gentle phenomena we observe in nature. Morning dew forms when cooling air reaches the point where vapor pressure equals saturation pressure, forcing excess water molecules to condense onto surfaces. The same principle governs the formation of clouds at specific altitudes where temperature and pressure conditions favor condensation. This molecular level process scales up to influence weather patterns across entire continents, demonstrating how microscopic interactions create macroscopic climate effects. Adiabatic processes describe what happens to air temperature as atmospheric pressure changes during vertical movement through the atmosphere. Rising air expands and cools at predictable rates, while sinking air compresses and warms following the same physical laws. This adiabatic cooling and warming occurs without any heat being added or removed from the air mass, relying solely on the pressure changes that occur with altitude differences. These adiabatic processes create many of the temperature patterns we observe in mountainous regions and explain why temperatures generally decrease with elevation. The consistent operation of adiabatic cooling has shaped mountain climates for millions of years, creating zones, the distinct vegetation and weather patterns that characterize altitude environments. Understanding A's high diabatic processes helps explain why mountain peaks often have clouds forming around them, even when surrounding areas remain clear. Saturation mixing ratio represents the maximum amount of water vapor that air can hold at a given temperature and pressure, creating a fundamental limit that governs humidity and precipitation processes. When air reaches its saturation mixing ratio, additional water vapor must condense into liquid droplets, forming clouds, fog, or precipitation. This saturation threshold changes dramatically with temperature, with warm air capable of holding exponentially more moisture than cool air. The relationship between temperature and saturation mixing ratio drives many important climate processes, including the formation of precipitation when air masses cool below their saturation point. It also explains why tropical regions can maintain such high humidity levels, while polar regions remain relatively dry even when surrounded by ice and snow. This fundamental atmospheric relationship has remained constant throughout Earth's climate history, providing a stable foundation for the water cycle. Potential temperature provides a way to compare air masses that exist at different pressures by calculating what their temperatures would be if they were all brought to the same pressure level. This concept helps meteorologists understand the true thermal characteristics of different air masses and predict how they will behave when they move to different altitudes or encounter other air masses. Potential temperature remains constant as air moves vertically in the atmosphere, making it a useful tool for understanding atmospheric stability. Air masses with similar potential temperatures tend to mix easily, while those with different potential temperatures resist mixing and create distinct boundaries called fronts. These potential temperature differences drive many of the weather patterns we experience, from gentle sea breezes to powerful storm systems. The concept demonstrates how fundamental physical principles govern atmospheric behavior in ways that create predictable climate patterns. Equivalent potential temperature includes the effects of moisture content in addition to temperature and pressure, providing an even more complete picture of an air mass's energy content. This measurement accounts for the latent heat energy stored in water vapor, which can be released during condensation processes. Air masses with high equivalent potential temperatures contain more total energy and can produce more vigorous weather when they encounter other air masses or undergo lifting processes. Understanding equivalent potential temperature helps explain why some weather systems produce heavy precipitation, while others remain relatively benign despite similar temperature and pressure patterns. The additional energy available from water vapor condensation can transform a mild weather disturbance into a significant storm system, demonstrating how moisture content influences the intensity of atmospheric processes. Geostrophic wind represents the theoretical wind speed and direction that would exist if pressure gradient force and Coriolis force were perfectly balanced, creating steady flow parallel to isobars without acceleration. While true geostrophic conditions rarely exist near Earth's surface due to friction and terrain effects, geostrophic wind provides a useful approximation of actual wind patterns in the middle and upper atmosphere, where surface friction becomes negligible. The concept of geostrophic balance helps explain why wind patterns often flow around pressure systems rather than directly from high to low pressure areas. This understanding forms the basis for many weather prediction techniques and helps explain the persistent circulation patterns that characterize different climate zones. The mathematical relationship between pressure gradients and geostrophic wind has remained constant throughout Earth's history, creating reliable patterns that life has adapted to over millions of years. Thermal wind describes how wind speed and direction change with altitude due to horizontal temperature differences in the atmosphere. Areas with strong horizontal temperature gradients produce significant thermal wind effects, while regions with uniform temperatures show little change in wind patterns with height. This three-dimensional aspect of atmospheric motion helps explain why weather conditions can vary dramatically between surface levels and higher altitudes. Thermal wind effects contribute to the formation and maintenance of jet streams, those fast-moving ribbons of air that guide weather systems across continents. The thermal wind relationship also influences the development of storm systems by creating wind shear conditions that can either enhance or suppress convective activity. Understanding thermal wind helps explain why atmospheric conditions at different levels must be considered together to fully understand weather and climate patterns. Vorticity measures the tendency of air to rotate around a vertical axis, providing insight into the spinning motions that characterize weather systems, from small dust devils to large hurricanes. Positive vorticity indicates counterclockwise rotation in the northern hemisphere, while negative vorticity represents clockwise motion. Changes in vorticity as air moves through the atmosphere help forecasters predict where new weather systems will develop and how existing systems will evolve. The conservation of vorticity as air masses move and change shape creates many of the curved flow patterns we observe in weather maps. When air flows around obstacles like mountain ranges or encounters changes in the Coriolis parameter, vorticity changes can trigger the development of new weather patterns downstream. This principle helps explain why certain geographic locations are prone to cyclone formation, and why weather patterns often follow predictable tracks across ocean basins. Divergence and convergence describe the horizontal spreading apart or coming together of air masses, creating vertical motion that drives many important weather processes. Surface convergence forces air upward, creating the lifting needed for cloud formation and precipitation. Upper-level divergence creates space for rising air and helps maintain surface low-pressure systems. The balance between convergence and divergence at different atmospheric levels determines whether weather systems intensify or weaken. These divergence patterns create the vertical motion that connects surface weather to upper atmospheric conditions, demonstrating how weather systems extend through the entire depth of the troposphere. Understanding divergence helps explain why some weather disturbances develop into significant storms while others dissipate quickly, and why certain atmospheric patterns favor active weather while others promote stable conditions. Quasi-geostrophic theory provides a mathematical framework for understanding how large-scale atmospheric motions develop and evolve over time periods of several days. This theoretical approach assumes that atmospheric flow remains close to geostrophic balance while allowing for the small departures from balance that create weather systems. The theory successfully explains many observed weather patterns and forms the basis for numerical weather prediction models. The quasi-geostrophic approximation demonstrates how small imbalances in otherwise steady atmospheric flow can grow into the weather systems we experience daily. These mathematical insights reveal the underlying order within apparently chaotic weather patterns and help explain why certain atmospheric configurations are more likely to produce significant weather events than others. Rossby waves represent large-scale atmospheric waves that propagate around the globe, creating the meandering patterns in upper-level flow that guide surface weather systems. These waves can become stationary for extended periods, creating persistent weather patterns that bring weeks of similar conditions to large regions. The wavelength and amplitude of Rossby waves influence everything from the track of storm systems to the development of blocking patterns that can cause unusual weather. The theory of Rossby wave propagation helps explain how atmospheric disturbances in one part of the world can influence weather patterns thousands of miles away, days or weeks later. These wave patterns connect regional weather to global atmospheric circulation, demonstrating how local climate conditions are part of a planetary scale system of atmospheric motion that has operated consistently for millions of years. Potential vorticity combines rotation and stratification effects into a single parameter that remains conserved as air moves through the atmosphere, making it particularly useful for understanding how weather systems develop and move. Air masses with different potential vorticity values tend to remain distinct even when they come into contact, creating the sharp boundaries associated with weather fronts and storm systems. The conservation of potential vorticity helps explain why certain atmospheric patterns persist for extended periods, and why weather systems often follow predictable paths as they move across continents. This principle also governs the formation of upper-level troughs and ridges that influence surface weather patterns, connecting different levels of the atmosphere through fundamental conservation laws that have operated throughout Earth's climate history. Isentropic analysis examines atmospheric structure by following surfaces of constant potential temperature, revealing the three-dimensional organization of air masses and the pathways along which they move. These isentropic surfaces often slope significantly with respect to constant pressure or altitude surfaces, showing how warm air overrides cool air and how different air masses maintain their distinct characteristics while moving through the atmosphere. Following isentropic surfaces helps meteorologists understand how moisture and other atmospheric properties are transported across large distances, explaining how weather conditions in one region can influence conditions far downstream. This analysis technique reveals the hidden structure of the atmosphere and demonstrates how air masses maintain their identity while participating in global circulation patterns. Baroclinic instability describes the process by which atmospheric temperature contrasts create the conditions necessary for storm system development. When horizontal temperature gradients become sufficiently strong, small perturbations in the atmospheric flow can grow into the wave disturbances that become cyclones and anticyclones. This instability mechanism converts the potential energy stored in temperature contrasts into the kinetic energy of moving weather systems. The theory of baroclinic instability explains why most significant weather systems develop along temperature boundaries and why certain seasons and geographic locations are more prone to storm development than others. This fundamental atmospheric process has operated throughout Earth's climate history, creating the dynamic weather patterns that prevent the atmosphere from settling into static equilibrium while maintaining overall climate stability. Barotropic processes occur when atmospheric density depends only on pressure, creating simplified flow patterns that help us understand basic atmospheric dynamics. In barotropic conditions, wind speed is constant with height, and weather systems maintain their structure as they move horizontally through the atmosphere. While truly barotropic conditions are rare in the real atmosphere, this idealized state provides insight into fundamental atmospheric behavior. Understanding barotropic dynamics helps explain why some weather patterns are more stable and predictable than others, and why atmospheric flow sometimes organizes into simple, large-scale patterns. The contrast between barotropic and baroclinic conditions illustrates how temperature structure influences atmospheric behavior and determines whether conditions favor steady flow or active weather development. Equivalent barotropic models represent atmospheric behavior by assuming that wind patterns at all levels have the same basic structure, differing only in intensity. This approximation works well for understanding large-scale circulation patterns and provides a foundation for more complex atmospheric models. The equivalent barotropic approach captures many essential features of atmospheric behavior while remaining mathematically tractable. These simplified models demonstrate how fundamental physical principles govern atmospheric motion and help explain why certain circulation patterns appear repeatedly in different geographic locations and time periods. The success of equivalent barotropic models in reproducing observed atmospheric behavior confirms that underlying physical laws create order within the apparent complexity of weather and climate systems. Planetary boundary layer dynamics govern the behavior of the lowest portion of the atmosphere, where surface effects directly influence air movement, temperature, and moisture content. This boundary layer typically extends from the surface up to about 1 to 2 kilometers altitude, encompassing the air that directly affects human activities and terrestrial ecosystems. The height and characteristics of the boundary layer change throughout the day and with different weather conditions. Surface friction within the planetary boundary layer reduces wind speeds and changes wind directions compared to the free atmosphere above. This friction also creates turbulence that mixes air vertically, distributing heat, moisture, and pollutants through the lower atmosphere. Understanding boundary layer processes is essential for predicting surface weather conditions and explaining how atmospheric conditions at the ground level differ from those just a few hundred meters higher. Entrainment processes describe how atmospheric boundary layers grow and mix with the air above them, creating the vertical exchange that connects surface conditions to the broader atmospheric circulation. During daytime heating, convective boundary layers expand upward by entraining air from the stable layers above, while nocturnal boundary layers often become very shallow as surface cooling suppresses vertical mixing. These entrainment processes help explain why pollution concentrations, humidity levels, and temperature patterns change throughout the day even when large-scale weather conditions remain steady. The daily cycle of boundary layer development and decay creates predictable patterns in surface weather that have remained consistent for millions of years, providing stable environmental cues that many species use for navigation and timing of daily activities. Convective available potential energy measures the amount of energy available for thunderstorm development when atmospheric conditions favor strong vertical air movement. High values of convective available potential energy indicate that air parcels lifted from the surface will accelerate upward rapidly, creating the strong updrafts needed for severe thunderstorm development. This energy comes from the temperature and moisture contrasts between and the surrounding atmosphere. Understanding air surface, some convective available potential energy helps explain why days produce violent thunderstorms, while others with seemingly similar conditions remain quiet. The energy available for convection varies with surface heating, moisture content, and atmospheric stability, creating daily and seasonal cycles in thunderstorm potential that influence regional climate patterns and water resources. Convective inhibition represents the energy barrier that must be overcome before thunderstorm development can begin, even when significant convective available potential energy exists in the atmosphere. This inhibition often takes the form of warm, dry air layers that prevent surface-based air parcels from reaching their level of free convection. Strong convective inhibition can suppress thunderstorm development despite favorable upper-level conditions. The balance between convective available potential energy and convective inhibition determines when and where thunderstorms will develop, helping explain the timing and location of afternoon and evening precipitation innates. This many-climate balance changes throughout the day as surface heating and atmospheric mixing alter the temperature and moisture structure of the lower atmosphere. Lifted condensation level represents the altitude at which rising air reaches saturation and begins to form clouds, marking the typical cloud base height for convective systems. This level depends on surface temperature and humidity conditions, with higher lifted condensation levels indicating drier surface air and lower levels suggesting moist conditions. The lifted condensation level provides a useful forecast tool for predicting cloud formation and precipitation potential. Understanding lifted condensation level helps explain why cloud base heights vary from day to day and location to location, and why some areas are prone to low-hanging clouds while others typically have high-based cumulus formations. This altitude also influences precipitation efficiency, with lower cloud bases generally favoring more effective precipitation processes. Level of free convection marks the altitude where rising air parcels become warmer than their surrounding environment and begin to accelerate upward under their own buoyancy. This level often coincides with the beginning of significant cloud development and marks the threshold between forced lifting and spontaneous convection. Air parcels that reach their level of free convection can continue rising rapidly if sufficient moisture and instability exist above. The relationship between lifted condensation level and level of free convection helps determine whether cloud development will remain shallow or grow into deep, precipitating systems. When these levels are close together, conditions favor efficient convective development, while large separations between them can inhibit significant vertical cloud growth. Equilibrium level represents the altitude where rising air parcels again become the same temperature as their environment, marking the typical top of convective cloud development. This level depends on the temperature profile of the atmosphere and the amount of latent heat released during condensation processes. The equilibrium level helps determine the vertical extent of thunderstorms and influences their precipitation efficiency and severity. Understanding equilibrium level explains why some thunderstorms remain relatively shallow while others grow into towering systems that can reach the stratosphere. The height of the equilibrium level also influences the types of precipitation that form, with higher levels generally favoring more diverse precipitation processes and potentially more severe weather. Downdraft processes in thunderstorms create the sinking air motion that baldrifances, yupts, and helps transport precipitation to the ground. These downdrafts form when precipitation loading and evaporational cooling create negatively buoyant air that accelerates downward. Strong downdrafts can produce damaging winds at the surface and help maintain thunderstorm circulation by providing low-level convergence that feeds continued updraft development. The balance between updraft and downdraft processes determines thunderstorm longevity and intensity, with optimal ratios favoring persistent, severe systems, while imbalanced conditions lead to rapid weakening. Understanding downdraft dynamics helps explain why some thunderstorms produce beneficial rainfall, while others create destructive wind and hail events. Microburst phenomena represent intense, localized downdrafts that can produce dangerous surface winds despite occurring relatively within small areas. These downdrafts form when evaporational cooling and precipitation loading create concentrated areas of sinking air that spread outward upon reaching the ground. Microbursts can produce surface winds exceeding hurricane force within areas just a few kilometers across. Recognition of microburst processes has improved aviation safety and weather prediction capabilities, demonstrating how understanding small-scale atmospheric phenomena contributes to broader climate science knowledge. These intense but localized events illustrate how atmospheric energy can concentrate into very small areas while remaining part of larger-scale circulation patterns. Mesoscale convective systems represent organized clusters of thunderstorms that can persist for many hours and influence weather patterns across hundreds of kilometers. These systems develop their own circulation patterns and can become semi-independent of the larger-scale atmospheric flow that initially triggered their formation. Mesoscale convective systems often produce the majority of warm season precipitation in continental regions. The self-organizing nature of mesoscale convective systems demonstrates how atmospheric processes can create order from apparent chaos, with individual thunderstorms interacting to form coherent, long-lasting weather patterns. Understanding these systems helps explain how local convective processes connect to regional climate patterns and contribute to seasonal precipitation distributions. Supercell thunderstorms represent the most organized and potentially severe form of convective weather systems, characterized by persistent, rotating updrafts that can maintain storm structure for many hours. These storms develop when atmospheric wind patterns create the rotation necessary for supercell formation, typically requiring specific combinations of wind shear and atmospheric instability. Supercells can produce large hail, dam maintaining their aging winds, and tornadoes while distinctive structure. The rotating nature of supercell storms allows them to move in directions different from the general atmospheric flow, sometimes following curved or erratic paths that can be difficult to predict. Understanding supercell dynamics helps explain how these relatively rare but significant weather events develop and provides insight into the most extreme examples of atmospheric convective processes. Mesocyclone circulation within supercell thunderstorms creates the organized rotation that can persist for hours, drawing energy from the contrast between different wind speeds and directions at various altitudes. This rotating column of air typically extends through the entire depth of the storm, creating a remarkably stable structure that can maintain itself even as it moves across changing terrain. The mesocyclone acts like an atmospheric engine, concentrating the energy from a large area into a focused column of circulation. The formation of mesocyclones requires precise atmospheric conditions that align wind patterns at multiple levels to create the necessary rotation. When these conditions occur, the resulting circulation can become so persistent that storms maintain their identity for extraordinary distances, sometimes traveling hundreds of miles while preserving their essential structure. This demonstrates how atmospheric processes can create remarkably stable patterns from seemingly chaotic initial conditions. Wall clouds form when mesocyclone circulation creates a localized area of strong upward air motion that draws moisture-laden air from lower levels into a concentrated updraft region. These distinctive cloud formations appear as lowered sections of the storm base, often rotating slowly and creating the dramatic visual signature that storm watchers recognize. Wall clouds represent areas where the atmosphere's vertical motion becomes so organized that it creates its own distinct cloud structure. The development of wall clouds often precedes other significant storm features, making them valuable indicators of atmospheric organization and potential severe weather development. These formations demonstrate how large-scale circulation patterns can create localized atmospheric phenomena that appear quite different from the surrounding cloud structure, showing the remarkable variety that emerges from fundamental atmospheric processes. Laminar flow describes atmospheric motion that occurs in smooth, parallel layers without the turbulent mixing that characterizes most weather systems. While truly laminar conditions are rare in the atmosphere due to surface heating and friction effects, understanding laminar flow helps explain how some atmospheric processes can maintain their organization across large distances. Laminar conditions typically occur in very stable atmospheric layers where temperature and wind patterns suppress vertical mixing. When laminar flow does occur, it can create remarkably clear and stable atmospheric conditions that persist for extended periods. These conditions often produce the crystal clear visibility and smooth air motion that pilots and meteorologists associate with high-pressure systems and stable atmospheric patterns. The contrast between laminar and turbulent flow illustrates how different atmospheric conditions can create dramatically different environmental experiences. Turbulent flow characterizes most atmospheric motion near Earth's surface, where surface heating, friction, and obstacles create the chaotic mixing that we experience as gusty winds and changing weather conditions. This turbulence plays a crucial role in mixing heat, moisture, and momentum throughout the lower atmosphere, preventing the development of stagnant layers that would create unhealthy air quality conditions. Turbulent mixing also helps distribute solar energy more evenly across different atmospheric levels. The scale of atmospheric turbulence varies enormously, from tiny eddies just centimeters across to large circulation patterns that span hundreds of kilometers. This range of turbulent scales creates the complex atmospheric mixing that supports weather formation while preventing the atmosphere from separating into completely distinct layers. Understanding turbulent processes helps explain why atmospheric conditions can change rapidly, even when large-scale weather patterns appear stable. Reynolds number provides a mathematical way to predict whether fluid flow will be laminar or turbulent based on the balance between inertial and viscous forces. In atmospheric applications, Reynolds numbers help meteorologists understand when and where turbulent mixing will occur and how atmospheric stability influences air motion patterns. High Reynolds numbers indicate conditions that favor turbulent flow, while low values suggest laminar conditions. The concept of Reynolds number applies to atmospheric phenomena, ranging from the flow around individual buildings to the motion of entire weather systems. This mathematical framework helps explain why some atmospheric conditions produce smooth, predictable air motion, while others create chaotic, rapidly changing flow patterns that make weather prediction more challenging. Kelvin-Helmholtz instability occurs when wind shear creates wave-like disturbances along the boundary between air masses, moving at different speeds. These instabilities often appear as distinctive cloud formations that resemble ocean waves, creating some of the most beautiful and recognizable cloud patterns in the sky. The wave-like structure develops when the velocity difference between adjacent air layers becomes large enough to overcome the stabilizing effects of density differences. These instabilities demonstrate how atmospheric motion naturally organizes itself into coherent patterns even under apparently that chaotic conditions. The waves developed from Kelvin-Helmholtz instability can grow and break, eventually creating turbulent mixing between the original air masses. This process helps explain how the atmosphere maintains its overall circulation patterns while continuously mixing different air masses. Clear air turbulence represents one of the most challenging aspects of atmospheric motion to predict and understand, occurring in apparently clear skies without indicators any visible weather. This turbulence typically develops in regions of strong wind shear, often near jet streams or in areas where different air masses meet at altitude. The invisible nature of clear air turbulence makes it particularly hazardous for aviation, while demonstrating how atmospheric motion can be highly active even when no clouds are present. The formation of clear air turbulence involves many of the same processes that create visible weather phenomena, but without the moisture needed for cloud formation. Understanding these invisible atmospheric motions helps explain how energy moves through the atmosphere and how apparently calm conditions can conceal significant atmospheric activity. This hidden turbulence plays an important role in mixing atmospheric layers and transporting momentum between different altitudes. Atmospheric gravity waves propagate through stable atmospheric layers when air is displaced vertically and then oscillates around its equilibrium position under the influence of buoyancy forces. These waves can travel horizontally for hundreds of kilometers, while maintaining their wave structure, creating ripple effects that can influence weather patterns far from their source. Mountain ranges often generate gravity waves that create distinctive cloud patterns and influence precipitation distributions. The study of atmospheric gravity waves reveals how disturbances in one part of the atmosphere can influence conditions in distant locations through wave propagation. These waves transport energy and momentum through the atmosphere, contributing to the complex interactions that connect local weather phenomena to larger-scale circulation patterns. Understanding gravity wave processes helps explain some of the apparent connections between geographically separated weather events. Waves form on the downwind side of mountain ranges when stable air flows over elevated terrain, creating standing wave patterns that can extend for many kilometers downstream from the mountains. These waves often produce distinctive lenticular clouds that appear to remain stationary even though air continuously flows through them. Lee wave systems can create severe turbulence and strong downdrafts that significantly affect aviation and local weather patterns. The formation of Lee waves depends on the stability of the atmospheric layers and the speed of the wind flowing over the mountains. When conditions are optimal, these wave systems can become very pronounced, creating some of the most dramatic cloud formations and turbulent conditions found anywhere in the atmosphere. Lee waves demonstrate how topographic features continue to influence atmospheric motion long after the air has passed over the original obstacle. Mountain wave systems can extend vertically through the entire depth of the troposphere and into the stratosphere, creating atmospheric disturbances that reach altitudes far above the mountains that generate them. These vertical wave propagations can influence jet stream patterns and upper-level atmospheric circulation, showing how surface topography affects atmospheric motion at all altitudes. Strong mountain wave events can create turbulence and wind patterns that affect weather hundreds of kilometers away from the original mountain range. The energy contained in mountain wave systems comes from the kinetic energy of the horizontal wind flow, which gets converted into vertical wave motion as air encounters the mountain barrier. This energy conversion process can be highly efficient, creating mountain waves with amplitudes much larger than the original mountain height. Understanding mountain wave dynamics helps explain how topographic features influence regional climate patterns and contribute to the atmospheric mixing that affects global circulation. Hydraulic jump phenomena in the atmosphere create dramatic changes in flow characteristics when fast-moving air encounters obstacles or changes in terrain elevation. These atmospheric hydraulic jumps can produce standing waves, rotors, and other complex flow patterns that create hazardous conditions for aircraft, while demonstrating the fundamental fluid dynamics that govern atmospheric motion. The jump represents a transition from supercritical to subcritical flow conditions. Atmospheric hydraulic jumps often occur in association with mountain wave systems, creating regions of intense turbulence and rapidly changing wind conditions. These phenomena illustrate how atmospheric flow can undergo sudden transitions that create dramatically different conditions over very short distances. Understanding hydraulic jump processes helps explain some of the most extreme and localized atmospheric phenomena. Bore formation in the atmosphere creates propagating pressure disturbances that can travel for hundreds of kilometers while maintaining their wave structure. Atmospheric bores often develop when stable air layers create conditions similar to those found in shallow water wave systems, allowing pressure waves to propagate horizontally through the atmosphere. These bores can trigger thunderstorm development and create distinctive cloud formations. The study of atmospheric bores reveals connections between atmospheric dynamics and the fluid mechanics that govern other natural systems. These wave phenomena demonstrate how the atmosphere can support wave motions similar to those found in oceans and other fluid systems, showing the fundamental unity of fluid dynamic processes across different environments. Solitary wave solutions in atmospheric dynamics describe wave disturbances that maintain their shape while propagating through the atmosphere, neither growing nor decaying as they travel. These mathematical solutions help explain how certain atmospheric disturbances can maintain their identity over long distances and time periods, creating persistent weather patterns that influence regional climate conditions. Solitary waves represent a special class of atmospheric motion where non-linear and dispersive effects balance exactly. The existence of solitary wave solutions in atmospheric models demonstrates how complex atmospheric systems can support remarkably stable and persistent patterns of motion. These solutions provide into how atmospheric energy can become concentrated into coherent structures that resist the dissipative effects that normally cause weather patterns to decay over time. Non-linear wave interactions in the atmosphere create complex patterns of energy exchange between different wave modes, leading to phenomena that cannot be understood through linear wave theory alone. These interactions can cause waves to grow, decay, or change their propagation characteristics in ways that depend on the specific atmospheric conditions they encounter. Understanding nonlinear effects is essential for predicting how atmospheric disturbances will evolve over time. The mathematical treatment of nonlinear atmospheric waves reveals how small disturbances can sometimes grow into large-scale weather systems through energy transfer processes that concentrate atmospheric energy into increasingly organized patterns. These nonlinear effects help explain how atmosphere can spontaneously develop coherent structures like cyclones and anticyclones from apparently random initial conditions. Dispersive wave propagation occurs when different wavelength components of an atmospheric disturbance travel at different speeds, causing wave packets to spread out as they propagate through the atmosphere. This dispersion affects how atmospheric energy moves between different locations and how disturbances maintain their coherence over long distances. Dispersive effects are particularly important for understanding how atmospheric gravity waves influence large-scale circulation patterns. The balance between dispersion and nonlinear effects determines whether atmospheric waves will maintain their original form, grow into larger disturbances, or break up into smaller-scale turbulence. Understanding these competing effects helps explain why some atmospheric patterns persist for extended periods while others decay rapidly, contributing to the overall predictability of weather and climate systems. Phase-speed relationships for atmospheric waves determine how quickly different types of disturbances propagate through the atmosphere and how they interact with the background atmospheric flow. Waves that move faster than the mean flow can outrun the conditions that created them, while slower-moving waves can be trapped and amplified by the atmospheric patterns they encounter. These speed relationships help explain the geographic distribution of different types of weather phenomena. Group velocity describes how wave energy propagates through the atmosphere, which can be quite different from the phase speed of individual wave crests. Understanding group velocity helps explain how atmospheric energy moves from one location to another and how local weather disturbances can influence conditions in distant areas through wave propagation effects. Critical layer interactions occur when atmospheric waves encounter regions where their phase speed matches the local wind speed, creating conditions where wave energy can be absorbed or reflected by the atmospheric flow. These interactions play crucial roles in determining how atmospheric waves propagate vertically through the atmosphere and how they influence circulation patterns at different altitudes. Critical layers often mark boundaries where wave propagation characteristics change dramatically. The absorption of wave energy at critical layers helps explain how momentum and energy are transferred between different parts of the atmospheric circulation system. These transfer processes are essential for maintaining the overall atmospheric circulation and help explain how disturbances in one part of the atmosphere can influence conditions at completely different altitudes or locations. Wave-mean flow interactions describe how propagating atmospheric waves can modify the average atmospheric circulation, while changes in the mean flow can affect wave propagation characteristics. These interactions create feedback loops that couple different scales of atmospheric motion, from small-scale gravity waves to planetary-scale circulation patterns. Understanding these interactions is essential for predicting how atmospheric circulation patterns will evolve over time. The mathematical treatment of wave-mean flow interactions reveals how atmospheric systems naturally tend toward certain equilibrium states that balance wave activity with mean circulation patterns. These equilibrium states help explain the persistence of certain atmospheric patterns and the predictability of seasonal climate variations. Eliason palm flux diagnostics provide a mathematical framework for understanding how atmospheric waves transport momentum and energy through the circulation system, revealing the pathways by which small-scale wave activity influences large-scale atmospheric patterns. These diagnostic tools help meteorologists understand how different types of atmospheric waves contribute to the maintenance of jet streams, storm tracks, and other climatologically important circulation features. The analysis of Eliason palm fluxes shows how atmospheric wave activity connects different regions and altitudes through momentum and energy transport processes. These connections help explain how local weather phenomena can have far-reaching effects on atmospheric circulation and how changes in wave activity can influence climate patterns on seasonal and longer time scales. Sudden stratospheric warming events demonstrate how wave-mean flow interactions can dramatically alter atmospheric circulation patterns, sometimes causing the polar vortex to weaken or reverse completely within a matter of days. These events illustrate the remarkable sensitivity of atmospheric circulation to wave activity and show how relatively small changes in wave propagation can trigger major circulation reorganizations that affect weather patterns throughout the hemisphere. Understanding sudden stratospheric warming helps explain some of the most dramatic examples of atmospheric variability and demonstrates how different layers of the atmosphere are connected through wave propagation processes. These events also show how atmospheric circulation can undergo rapid transitions between different stable states, creating the potential for sudden changes in regional climate patterns. Quasi-biennial oscillation represents a regular cycle in equatorial stratospheric winds that alternates between easterly and westerly phases approximately every 2 years, creating one of the most predictable patterns in atmospheric circulation. This oscillation is driven by the interaction between atmospheric waves and the mean flow, demonstrating how wave-mean flow interactions can create persistent, large-scale circulation patterns that influence global atmospheric circulation. The predictability of the quasi-biennial oscillation shows how certain aspects of atmospheric circulation follow regular patterns, despite the generally chaotic nature of weather systems. Understanding this oscillation helps explain connections between equatorial atmospheric processes and weather patterns in other parts of the world, demonstrating how tropical atmospheric dynamics influence global climate patterns. Madden-Julian oscillation describes a slow-moving pattern of enhanced and suppressed tropical precipitation that propagates eastward around the globe with a period of approximately 30 to 60 days. This oscillation represents one of the dominant sources of atmospheric variability on sub-seasonal timescales and influences weather patterns far beyond the tropical regions where it originates. The oscillation affects monsoon systems, hurricane activity, and temperature patterns across much of the globe. Understanding the Madden-Julian oscillation helps explain how tropical atmospheric processes can influence weather patterns in temperate and polar regions through teleconnection patterns that span the entire globe. This oscillation demonstrates how atmospheric circulation naturally organizes itself into coherent, large-scale patterns that persist for weeks or months while slowly propagating around the planet. Teleconnection patterns describe statistical relationships between atmospheric conditions in widely separated geographic regions, revealing how local weather patterns connected to global are. These patterns show variations in scale circulation, how atmospheric waves and circulation changes can create correlations between weather conditions in different parts of the world, sometimes linking regions that seem to have no obvious physical connection. The study of teleconnections has revealed how atmospheric circulation creates a complex network of interactions that connect local weather to global climate patterns. Understanding these connections helps explain why weather patterns in one region can be influenced by atmospheric conditions thousands of kilometers away, and why certain combinations of regional weather patterns tend to occur together. Arctic oscillation describes variations in atmospheric pressure patterns over the Arctic that influence temperature and precipitation patterns throughout the Northern Hemisphere. When the Arctic oscillation is in its positive phase, strong low pressure over the Arctic helps keep cold air confined to polar regions. During negative phases, weaker pressure gradients allow Arctic air to spread into temperate latitudes, creating colder than normal conditions across large areas. The Arctic oscillation demonstrates how atmospheric circulation patterns in polar regions can influence weather conditions across entire continents, showing the global reach of Arctic climate processes. Understanding this oscillation helps explain some of the year-to-year variability in winter weather patterns and provides insight into how Arctic climate changes might affect weather patterns in more populated regions. North Atlantic oscillation represents changes in the atmospheric pressure difference between the Icelandic low and Azores high pressure systems, creating variations that influence weather patterns across Europe and eastern North America. The strength and position of these pressure systems determines storm tracks across the North Atlantic and affects everything from European winter temperatures to precipitation patterns along the eastern seaboard of North America. The persistence of North monthly Atlantic oscillation patterns onto seasonal timescales provides some predictability for regional climate conditions, helping explain why certain winters are consistently mild or severe across large geographic areas. This oscillation shows how relatively simple changes in atmospheric pressure patterns can have far-reaching effects on regional weather and climate. Pacific decadal oscillation describes long-term variations in North Pacific sea surface temperature patterns that can persist for decades, creating sustained changes in atmospheric circulation patterns that affect weather and climate across much of North America and the Pacific Basin. Unlike shorter-term oscillations, the Pacific decadal oscillation represents climate variability on timescales that can span entire human generations. Understanding the Pacific decadal oscillation helps explain some of the long-term trends in regional climate that cannot be attributed to shorter-term weather variability. This oscillation demonstrates how ocean-atmosphere interactions can create climate patterns that persist much longer than typical weather phenomena, bridging the gap between short-term weather and long-term climate change. Atlantic multidecadal oscillation represents variations in North Atlantic sea surface temperatures that occur on timescales of several decades, influencing hurricane activity, Sahel precipitation, and temperature patterns across the Atlantic basin. These long-term oceanic variations create sustained changes in atmospheric circulation that can affect regional climate patterns for periods much longer than typical weather cycles. The study of multi-decadal oscillations reveals how ocean-atmosphere interactions can create climate variability that spans multiple decades, showing how current climate conditions may be influenced by oceanic changes that began years or even decades ago. Understanding these long-term patterns helps explain some of the apparent trends in regional climate that might otherwise be attributed to other causes. El Niño Southern Oscillation represents the most significant source of year-to-year climate variability on Earth, creating changes in tropical Pacific conditions that influence weather patterns across much of the globe. During El Niño events, warm ocean temperatures in the eastern Pacific alter atmospheric circulation patterns, typically bringing increased precipitation to some regions while creating drought conditions in others. La Niña events create opposite effects, with cooler than normal eastern Pacific temperatures. The global reach of El Niño Southern Oscillation effects demonstrates how ocean-atmosphere interactions in one region can influence climate conditions worldwide through atmospheric teleconnection patterns. Understanding this oscillation provides some of the most reliable sources of seasonal climate prediction, showing how tropical Pacific conditions can be used to forecast regional weather patterns months in advance. Indian Ocean Dipole describes variations in sea surface temperature patterns across the Indian Ocean that can influence monsoon systems and regional climate patterns throughout the Indian Ocean basin. Like other ocean-atmosphere oscillations, the Indian Ocean Dipole creates sustained changes in atmospheric circulation that affect precipitation and temperature patterns across large geographic areas for periods of several months to years. The recognition of Indian Ocean dipole effects has improved understanding of how multiple ocean basins interact to influence global climate patterns, showing how atmospheric circulation connects oceanic variations in different regions. This oscillation helps explain some of the variability in monsoon systems and demonstrates how regional climate patterns are influenced by global-scale ocean-atmosphere interactions. Southern Annular Mode describes variations in the strength and position of the circumpolar atmospheric circulation around Antarctica, creating changes that influence weather patterns throughout the Southern Hemisphere. When the Southern Annular Mode is in its positive phase, stronger westerly winds around Antarctica tend to keep cold air confined to polar regions. Negative phases allow cold Antarctic air to penetrate into temperate latitudes more frequently. Understanding the Southern Annular Mode helps explain climate variability in the Southern Hemisphere and demonstrates how atmospheric circulation patterns around Antarctica influence weather conditions across the entire southern half of the globe. This mode shows how polar atmospheric processes can have far-reaching effects on regional climate patterns throughout the southern hemisphere. Blocking patterns occur when atmospheric flow becomes stationary for extended periods, creating persistent weather conditions that can last for weeks or even months. These patterns develop when the normal westerly flow of the jet stream becomes disrupted, creating large-scale meanders that remain fixed in place rather than progressing eastward. During blocking events, regions can experience prolonged periods of the same weather type, whether it's extended heat waves, persistent cool conditions, or unusual precipitation patterns. The formation of blocking patterns represents one of nature's most remarkable examples of atmospheric persistence, where dynamic systems that normally change rapidly become locked into stable configurations. High-pressure ridges and low-pressure troughs that would typically move across continents in a matter of days can become anchored in position, creating weather patterns that seem to defy the normal progression of seasons. These blocking events demonstrate how atmospheric circulation can spontaneously organize itself into quasi-permanent structures. Atmospheric blocking affects not just local weather, but can influence circulation patterns across entire hemispheres, creating ripple effects that connect weather conditions in widely separated regions. When the normal flow of the jet stream becomes blocked in one area, it often creates compensating circulation changes elsewhere, linking weather patterns across thousands of miles through the mathematical precision of atmospheric dynamics. Zonal flow describes atmospheric circulation patterns where winds blow primarily from west to east, creating relatively straight jet stream configurations that allow weather systems to move rapidly across continents. These zonal patterns tend to produce more predictable weather with systems that follow regular tracks and maintain consistent characteristics as they travel. Zonal flow represents the atmosphere's most efficient mode for transporting energy and momentum between different regions. During strong zonal flow periods, temperature gradients between different latitudes remain relatively moderate, because the rapid west-to-east transport of air masses prevents extreme cold or warm conditions from persisting in any one location for extended periods. This creates the steady march of weather systems that characterizes many temperate climate regions, with storms developing, intensifying, and dissipating in regular cycles as they move along predictable paths. Meridional flow patterns feature large north-south components in atmospheric circulation, creating the meandering jet stream configurations that bring more variable and extreme weather conditions. These patterns develop when the normal zonal flow becomes disrupted, allowing cold polar air to penetrate far into temperate regions, while warm tropical air extends toward higher latitudes. Meridional patterns often persist longer than zonal ones, creating sustained periods of unusual weather. The mathematical description of meridional flow reveals how atmospheric energy can become concentrated into large-scale wave patterns that amplify as they develop, sometimes creating circulation anomalies that extend from the surface to the top of the troposphere. These patterns demonstrate how relatively small changes in atmospheric flow can grow into major circulation reorganizations that affect weather patterns across entire continents. Planetary wave patterns represent the largest scale atmospheric motions, with wavelengths that span entire hemispheres in periods that can extend from weeks to months. These waves arise naturally from the rotation of the Earth and the distribution of land masses and oceans, creating preferred patterns of atmospheric circulation that tend to recur in similar forms year after year. Planetary waves provide the framework within which smaller-scale weather systems develop and move. The amplitude and position of planetary waves determine many aspects of regional climate, from the average tracks of storm systems to the typical temperature and precipitation patterns that define different geographic regions. Changes in planetary wave patterns can shift entire climate zones, bringing unusual weather to regions that normally experience very different conditions. Understanding planetary waves helps explain how atmospheric circulation connects local weather to global climate patterns. Stationary wave patterns describe atmospheric configurations where planetary waves remain fixed relative to Earth's surface, creating persistent circulation features that influence regional climate over extended periods. These patterns often develop in response to the distribution of continents and oceans, mountain ranges, and seasonal heating patterns, creating semi-permanent circulation features that define regional climate characteristics. The study of stationary waves reveals how geographic after-air masses have passive features continue to influence atmospheric circulation longed over them, creating downstream effects that can persist for thousands of kilometers. These patterns show how the solid Earth shapes atmospheric motion through topographic and thermal forcing, demonstrating the intimate connection between surface geography and atmospheric circulation. Transient wave activity describes the propagating disturbances that carry energy and momentum through the atmospheric circulation system, creating the day-to-day weather variability that we experience as changing conditions. These waves include everything from individual storm systems to the wave packets that modulate larger-scale circulation patterns. Transient waves are responsible for most of the short-term predictability in weather systems. The interaction between transient and stationary wave components creates much of the complexity we observe in atmospheric circulation, with propagating disturbances modifying persistent patterns while being influenced by the background circulation through which they move. Understanding these interactions helps explain how weather systems can sometimes behave predictably, while at other times seeming to develop chaotic characteristics. Storm track climatology examines the preferred pathways that weather systems follow as they move across different geographic regions, revealing the underlying circulation patterns that guide cyclones and anticyclones along characteristic routes. These storm tracks represent statistical summaries of countless individual weather systems, showing where storms typically develop, intensify, and dissipate over periods of years or decades. The seasonal migration of storm tracks creates much of the annual cycle of weather patterns that defines regional climates, with winter storm tracks typically located farther south than summer tracks in most regions. Changes in storm track positions can dramatically alter regional precipitation and temperature patterns, showing how relatively small shifts in atmospheric circulation can have large impacts on regional climate conditions. Cyclogenesis processes describe how new low-pressure systems develop from initially weak atmospheric disturbances, growing into the organized circulation systems that bring much of our active weather. These development processes require specific combinations of atmospheric instability, moisture availability, and circulation patterns that favor the concentration of atmospheric energy into rotating systems. Understanding cyclogenesis helps explain why some weather disturbances develop into significant storms, while others remain weak and disorganized throughout their life cycles. The mathematical description of cyclogenesis reveals how atmospheric energy becomes concentrated through feedback processes that amplify initial disturbances, creating the organized circulation patterns that define mature cyclonic systems. Cyclolysis represents the dissipation phase of cyclonic systems, when organized circulation patterns weaken and eventually merge back into the larger scale atmospheric flow. This dissipation process occurs when the energy sources that maintain cyclonic circulation are removed or when atmospheric conditions no longer favor the maintenance of organized rotation. Understanding cyclolysis helps explain the finite lifetime of weather systems. The balance between cyclogenesis and cyclolysis processes determines the overall population of active weather systems in the atmosphere at any given time, creating statistical relationships between atmospheric energy sources and the frequency of different types of weather patterns. These processes show how the atmosphere naturally regulates its own activity levels through feedback mechanisms that balance system generation and decay. Frontogenesis describes how temperature and moisture boundaries sharpen and intensify within atmospheric circulation patterns, creating the distinct air mass boundaries that define weather fronts. This process occurs when circulation patterns act to increase horizontal temperature gradients, concentrating thermal contrasts into narrow zones where active weather development becomes favorable. The mathematical description of frontogenesis reveals how atmospheric circulation naturally tends to create sharp boundaries between different air masses, even when initial temperature differences are relatively gradual. This process demonstrates how atmospheric motion can spontaneously organize itself into coherent structures that persist despite the dissipative effects that normally smooth out atmospheric gradients. And so we reach the end of our gentle journey through the vast and peaceful systems that cradle our world. Tonight you've traveled with water vapor as it rises from warm oceans and falls as mountain snow. You've felt the slow breathing of forests and the ancient patience of ice. You've witnessed the delicate dance of pressure systems that bring tomorrow's weather and the quiet circulation patterns that have guided life for millions of years. These climate truths remind us that we live within something far larger and more stable than the daily headlines might suggest. Sleep well, knowing that these gentle forces continue their eternal work, keeping our planet in perfect balance.